So welcome students. So in this class, we will be dealing with a very important concept in chemistry, which is known as the mole concept. The mole can be defined as the amount of a substance that contains exactly 6.022140076 into 10 raised to 23 elementary entities. Now, this number, which can be approximated to 6.023 into 10 raised to 23, is known as the Avogadro constant, usually represented by the symbol Na. Now, the number of moles, if you want to calculate the number of moles of any substance, this equation can be used. So, small n indicates the number of moles of a substance, and capital N is the total number of elementary entities in the sample, and Na is the Avogadro constant. Okay. So if you want to calculate the number of moles of any substance, just divide the total number of elementary entities in the sample with Na. So if you have for example, if you want to calculate how many dozens of eggs are there, if you have 24 eggs, how many dozens does it have? So if you want, a dozen means 12. So you divide the total number of eggs, that is 24, with 12. So 24 by 12, which is 2. So that means the 24 eggs means 2 dozen. So this is the same principle that we are using here. The number of moles N can be calculated by using the formula capital N divided by Na, which is the Avogadro constant. N is the total number of elementary entities in the sample, and Na is the Avogadro constant. So by using this ratio, you can give the total number of moles of the substance. And the mole concept is a fundamental principle in chemistry that serves as a bridge between the atomic and macroscopic worlds. It allows chemists to quantify substances in terms of the number of particles, such as atoms, molecules, or ions, by relating this count to a measurable quantity of matter. 1 mole of any substance contains Avogadro number, which is approximately 6.023 into 10 raised to 23 of representative particles. This concept simplifies the expression of chemical reactions, enabling calculations based on mass, volume, and concentration. By using the mole, chemists can predict how much of a substance will react or be produced, making it essential in stoichiometry and various other chemical calculations. So this is the basis of the mole concept. Now, a mole means, if I say 1 mole, it indicates that it contains Avogadro number of entities, that is 6.023 into 10 raised to 23. Now, when I say 1 mole, I need to say 1 mole of what? I need to say it is 1 mole of atoms, or 1 mole of molecules, or 1 mole of ions. So I need to represent, if I just say a number 2, it doesn't make any sense. I need to say represent 2 of what? If I have 2 pencils, I say I have 2 pencils. If I just specify a number, that doesn't make any sense. So I need to specify what, how much of what. So like that, if I say just say 1 mole, it doesn't mean anything. No, it doesn't make any sense. I need to say 1 mole of what? 1 mole of, whether I say 1 mole of molecules, or what type of molecules. I mean, if I say 1 mole of oxygen molecules, or 1 mole of oxygen atoms, or 1 mole of water molecules, I need to say what I'm representing here by meaning 1 mole. So that's very important. Then the mole concept, if I say a mole of water contains Avogadro number of water molecules. However, each water molecule contains 2 hydrogen atoms and 1 oxygen atom. Therefore, 1 mole of water, H2O, contains 2 moles of hydrogen atoms and 1 mole of oxygen atoms. This is what I say. If I say 1 mole of water molecules, that means I have 1 mole of H2O at hand, or in a vessel. But 1 mole of water molecules actually contains 2 moles of hydrogen atoms and 1 mole of oxygen atom, because water molecule is represented by the formula H2O, which indicates that 1 molecule of water contains 2 hydrogen atoms and 1 oxygen atom. So if I say I have 1 mole of water molecules, that actually means that also indicates that I have 2 moles of hydrogen atoms and 1 mole of oxygen atom in 1 mole of water molecule. So keep that in mind. Likewise, if I say I have 1 mole of oxygen molecules, that indicates that I have 6.023 into 10 raised to 23 oxygen molecules. Now, an oxygen molecule is made up of 2 oxygen atoms. 2 oxygen atoms combine to form an oxygen molecule, that is O2. So if I say I have 1 mole of oxygen molecule, that is 6.023 into 10 raised to oxygen molecule, that means I have 2 moles of oxygen atoms. That is 2 into 6.023 into 10 raised to 23 oxygen atoms. Because 1 oxygen molecule is made up of 2 oxygen atoms. So if I just say 1 mole of oxygen, I need to say, I'm representing whether I'm saying about oxygen molecule or saying about oxygen atoms. So I need to clearly specify I have 1 mole of oxygen molecule. Now, if I say 2 moles of oxygen atoms, like that, I need to represent, or just mentioning I have 1 mole of oxygen doesn't make any sense. I need to say whether it is atom or molecule or ions that I'm specifying. So keep that also in mind. Now, the atomic mass, you already might have heard about the term oxygen, atomic mass. Atomic mass of an element is the mass of 1 atom of the element expressed in atomic units. So, an atomic mass of an element is the mass of 1 atom of the element expressed in atomic mass units, which is abbreviated as AMU. The mass of an atom is actually the mass of protons, total mass of the protons and neutrons present in an atom. You need not consider the mass of an electron, because mass of the electron is 2,000 times less than the mass of a proton or a neutron. So it's just 1 by 2,000, the mass of a proton or neutron. So we can consider electrons have negligible mass, or you just neglect the mass of the electron. So you just, when you take the total mass of an atom, you just add up the total mass of protons and neutrons. That means you just need to consider the total mass of the nucleons. That is, the total mass of the atom is equal to the total mass. It's the nucleus of the atom, because electrons are revolving around the nucleus. And the nucleus is made up of protons and neutrons. So you just consider the mass of the nucleons, or the total mass of the nucleus will be equal to the total mass of an atom. Now, in atomic mass units, the mass of a proton is taken as 1 AMU, and the mass of a neutron is also approximately 1 AMU. So if you have 1 proton and 1 neutron in an atom, the total mass of the atom will be 2 AMU. So you have 2 protons and 2 neutrons in an atom, total mass will be 4 AMU, because mass of 1 proton is 1 AMU and mass of 1 neutron is also 1 AMU. So 2 protons and 2 neutrons will add up to 4 atomic mass units, AMU. So you can just write that the total mass of the atom is equal to the total mass of the nucleons present in the atom. Okay. An atomic mass unit is usually abbreviated as AMU, or it's also indicated by the symbol small u. So if you take the atomic mass of a carbon, atomic mass of carbon is 12.011 atomic mass units. Now, why this ratio? Why it's not a whole integer? So if you have a proton and neutron and its value or mass is 1 each, then why the mass of a carbon atom is 12? If you take a carbon atom, it consists of 6 proton and 6 neutron. So total mass should be 12. But that's not the case. I'm saying that the atomic mass of a carbon is not a whole number. It is a ratio. It's just actually having a decimal place, 12.011. Why is that? That is because a carbon has isotopes. For example, the carbon 12 is the most common isotope of carbon, that is a common carbon, which actually is the common carbon, or the carbon-12 makes up 98.89% of the carbon in the whole Earth, or in the whole environment, and 1.11% of the total carbon is actually carbon-13. And it can also contain trace amounts of carbon-14 as well. So we can just neglect carbon-14, which is also only present in trace amounts. So the carbon actually consists of 98.89% of carbon-12 isotope and 1.11% of carbon-13. So if you want to take the atomic mass of carbon, we actually consider carbon-12 as well as carbon-13 and the relative percentage. So carbon-12 is present in 98.89 and carbon-13 is present in 1.11%. So the atomic mass of carbon can be calculated using this formula: 12 into, that is a carbon-12 isotope, which has an atomic mass of 12 AMU, into, and this relative percentage, it is 98.89 divided by 100, plus, what is the relative percentage of carbon-13? That is 13 into 1.11 divided by 100. So this will make up 11.8668, and this value is 0.1443. So when you add these two values, you get 12.0111. So that is the atomic mass of carbon-12. So if you want to know what is atomic mass of carbon-12 isotope specifically, that means it will be 12. What is atomic mass of carbon-13 isotope? It will be 13. It will always be a whole number. If we just saying without any specifying any isotope, what is the atomic mass of carbon, that will not be a whole number. Similarly, the case of oxygen, because oxygen in the atmosphere is made up of oxygen 16, which is a common isotope. When I say oxygen 16, it's actually specifying the mass number. Oxygen 16, because oxygen atomic number is fixed because its atomic number is 8. If it's oxygen 16, it also contains oxygen 17 as well. Now, so when you consider atomic mass of oxygen, you need to consider the several isotopes. Likewise, any element, if you take, we want to take the atomic mass of any element, you need to consider its relative percentage of the isotopes. So the atomic mass will always come out to be it doesn't come out to be a whole number, it will always be having a decimal place like that. So that is the point. If we want to just specify the atomic mass of an isotope, it will always be a whole number. So this is how you calculate the atomic mass. And so the molecular mass of an, what will be the molecular mass? I mentioned about atomic mass. What about the molecule? The molecular mass of an element is the sum of the atomic masses of all its constituents. For example, if you want to calculate the molecular mass of water, one molecule of water is made up of 2 hydrogen atoms and 1 oxygen atom. So if you have a hydrogen atom, if the mass of one hydrogen atom is 1 AMU, I'm just considering the common hydrogen atom, which is protein. I'm not considering its isotope like deuterium or tritium, which I discussed in the previous class. Just consider protein, it's common isotope. So protein is made up of just a single proton. It does not contain any neutron in its nucleus. So mass of a hydrogen atom or protein will be 1 AMU. So if you have 2 hydrogen atoms, the total mass will be 2 AMU. What about the mass of an oxygen atom? If you consider just oxygen 60, that's a common isotope of oxygen. Its atomic mass will be 16. So what will be the molecular mass of water? That is 2 plus 16, that's 80 AMU. So the mass of water molecule will be 80. What about the, likewise, what will be the mass of an oxygen molecule? An oxygen molecule is made up of 2 oxygen atoms. So the mass of an oxygen molecule will be 16 plus 16, that is 32 AMU. So like that, you can calculate the molecular mass of any element if you know its chemical formula. Okay. So this is how you calculate the molecular mass. You just add up the atomic masses of the atoms present in that molecule. So molecular mass of an element is the sum of the atomic masses of its constituent elements. The mass of 1 mole of an element will be equal to its atomic mass in grams. So what will be the mass of a 1 mole of an element? If I say 1 mole of oxygen, what will be its atomic mass? Just if I say one mole of, sorry, if I say 1 mole of oxygen atom, what is its weight? So how will you calculate it? The mass of 1 mole of an element will be equal to its atomic mass in grams. So if you have 1 mole of oxygen atom, how will you calculate its weight? Say an oxygen atom mass will be 16 m. So if you have 1 mole of oxygen atoms, please listen and understand it clearly. So if you have 1 mole of oxygen atoms, it means the weight will be equal to its atomic weight expressed in grams. An atomic weight of oxygen is 16 AMU. So if you have 1 mole of oxygen atoms, its total mass will be 16 grams. So it's very simple. Just convert the unit to grams. So if you have 1 mole of oxygen molecule, what will be its weight? 1 mole of oxygen molecule weight, if I need to calculate, what's the weight of 1 molecule of oxygen molecule, which is 32 m. So if you have 1 mole of oxygen molecules, its weight will be 32 grams. And what if someone asks what will be the weight of 1 mole of water molecule or 1 mole of water molecules? So one molecule of water weight is 18 m. So if you have 1 mole of water molecules, its total weight will be 18 grams. So we can calculate the weight of any element or molecule using this concept. So you have, if someone says I have 3 moles of water molecules, what its weight? 1 mole of water molecule weighs 18 grams. So what total weight of 3 moles of water molecule will be? It's simple, 3 into 18 grams. So yes, 54 grams. So we can calculate it. What will be the weight of 0.5 moles of water molecule? 1 mole of water is 18 grams. So 0.5 means half of that, 9 moles. So this is a very simple concept. So mass of 1 mole of an element will be equal to its atomic mass in grams. And how will you calculate total number of molecules? Mass of the sample divided by molar mass. So this will give the total number of moles. Mass of the sample divided by molecular mass. So for example, I have 56 grams of water. What is its number of moles? How do you calculate the number of moles of water molecule? 56 divided by the molecular mass of water, which is 18. 1 mole of water weighs 18 grams. So 56 grams divided by 18 grams. That will give 3 moles. Very simple concept. So total number of moles will be the mass of the sample divided by mass of the sample in grams divided by molar mass. Molar mass will be always, that is, molar mass means mass of 1 mole of that particular element. So mass of the sample divided by molar mass. So molar mass will be always expressed in grams. So mass of the sample in grams divided by the molar mass will give the number of moles. So the number of atoms or molecules will be equal to the number of moles into 6.023 into 10 raised to 23 or 6.022. It's correct. So the number of atoms, now we're going to calculate the number of atoms or molecules. Just multiply the number of moles of that particular atom or molecule into with 6.023 into 10 raised to 23. That will give the total number of any atom or molecules. And what will be the mass of 1 AMU in grams in SI unit? 1 AMU is 1 divided by 6.023 into 10 raised to 23. That is 1 divided by, actually 1 AMU is the reciprocal of the Avogadro number, and that is comes around 1.66 into 10 raised to minus 24 grams. So if I say 1 AMU, weight in grams will be around 1.66 into 10 raised to minus 24. So this is how you convert the number of moles to weight or back to the number of moles. So it's a very simple concept. See, when I say 1 mole, I need to, as I said, I need to say whether it is atoms, molecules, or ions. So if someone asks, I have 1 mole of copper and 1 mole of carbon, which weighs more? Say that I have 1 mole of carbon in a carbon molecule or carbon atoms, 1 mole of carbon atoms in a particular vessel. In another vessel, I have 1 mole of copper atoms. And if someone asks, which weighs more, whether 1 mole of carbon is having higher weight or 1 mole of copper is having heavier. So how will you calculate? See, just consider the atomic mass of carbon and copper. Atomic mass of carbon is 12 AMU and atomic mass of copper is 63.5 AMU. So if I have 1 mole of carbon, its total weight to carbon atoms, its total weight will be 2 grams. And if I have 1 mole of copper atoms, its total weight will be 63.5 grams. So obviously, 1 mole of copper will be having will be way more than 1 mole of copper, 1 mole of carbon. 1 mole of carbon is just 12 grams. 1 mole of copper atoms will be 63.5. So this is the concept. The carbon mass, atomic mass of carbon is 12, atomic mass of copper is 63.5. For 1 mole of carbon is 12 grams, 1 mole of copper will be weighing 63.5. So this is how you calculate. And another important concept in chemistry is the STP, which is known as the standard temperature and pressure. It is also mentioned as NTP. STP or NTP. NTP stands for normal temperature and pressure. STP stands for standard temperature and pressure. Both are same. STP, the standard temperature and pressure, are reference conditions used to define the standard state of a substance. So if you want to specify the state of a substance, you need to specify the temperature and pressure. So it is always difficult to say the temperature and pressure, or we want to specify the state of a substance. So naturally, what we do is you take a standard condition. That has standard condition, that is specified temperature and pressure. That is known as the STP. Now, the standard temperature in STP is 0 degrees Celsius. It's not room temperature, which is 20. Room temperature, you can consider room temperature as 25 degrees Celsius. But in standard temperature conditions, standard temperature is 0 degrees Celsius. 0 degrees Celsius, that is 273.15 Kelvin. And the standard pressure is the atmospheric pressure, which is 100 kilopascal. That is 1 atmosphere. That is 110 raised to 5 pascal or 1 atmosphere is the standard pressure. So when you specify, when I say STP, keep in mind that the temperature is 0 degrees Celsius, that is 273 Kelvin, and pressure is 1 atmosphere, that is 10 raised to 5 pascal. These conditions are used as reference points to make consistent and comparable measurements of the physical and chemical properties of substances. So, we want to compare the state of different substances. The two substances should be in identical conditions. The temperature and pressure should be identical. So, usually, the temperature make calculations easier. Will usually consider the STP condition, that is standard temperature and pressure. So standard temperature and the STP condition is 0 degrees Celsius or 273 Kelvin. The standard pressure is the atmospheric pressure, which is 1 atmosphere or 10 raised to 5 pascal. Now in gases, any gas, irrespective of its atomic mass, occupies 22.414 liters of volume at STP conditions. That is, if you take 1 mole of any gas, it's irrelevant that of the nature of the gas. You can take any gas, whether it is oxygen, hydrogen, nitrogen, chlorine. If it is 1 mole and the condition is STP condition, that is 0 degrees Celsius and 1 atmosphere, each of these gases will be occupying the same volume, which is 22.414 liters. Now, this law is known as the Avogadro law. This value is constant for all gases at STP, and this law is called the Avogadro law. So, if we can take 1 mole of hydrogen molecules, at STP condition, volume will be 22.414 liters. 1 mole of oxygen molecule at STP condition will be occupying a volume of 22.414 liters. 1 mole of nitrogen molecules at STP condition will be occupying a volume of 22.414 liters. And this law is known as the Avogadro law. In other words, we can say that the molar volume of a gas at STP is 22.41. Molar volume means volume occupied by 1 mole of a gas at STP condition. Yes, 22.414 liter, and this value is known as the molar volume of a gas at STP. The volume of a gas at STP is found with the relation PV is equal to nRT. This is known as the ideal gas equation. P stands for pressure, V stands for volume, N stands for the number of moles, R is the gas constant, which is 8.314 joules per moles per Kelvin, T is the temperature in Kelvin scale. So from that, we can, using this, which is known as the ideal gas equation, R is known as the universal gas constant because it is a constant for the same value for all the gases. PV is equal to nRT. From that, we can calculate the volume of pressure like that of a gas. And so this is the STP condition, and 28.414 is known as the molar volume. So 1 mole of a gas STP will occupy a volume of 22.414 liters. If I take 2 moles of the gas, its volume will be, that STP condition will be 22.4 into 2, that is 44.8. If I have 3 moles of gas at STP condition, its total volume will be 22.4 into 3. This is known as, so this is the Avogadro's law. So this is how you convert different constants. That is, you have 1 mole. If you have 1 mole of the gas, volume of the gas, which is 1 mole, that means it will be occupying a volume of 22.414 liters. And if I say 1 mole of any molecule, that means it contains 6.023 into 10 raised to 23 molecules. If I say 1 mole of atoms, it is 6.023 into 10 raised to 23 atoms. And what will be the molecular mass of 1 mole? That 1 mole will be weighing, which is the atomic mass expressed in grams. So 1 mole will be the molar mass, which is the molar mass. Atomic mass expressed in grams is known as the molar mass. So this is how you can convert different relations. If you have 1 mole, you can convert that. What is the mass of that 1 mole, or what is the volume occupied by that 1 mole, that particular substance. Okay. So keep in mind that 1 mole, if you want to find the volume, it should be a gas, not the solid or liquid, because that has specified volumes. A gas always expand. So that is 1 mole volume. With the gas, you want to consider the gas that is applicable only for gas. Avogadro law is applicable only for gases, not for solids or liquids. So this is how you convert the 1 mole into volume or number of particles or mass, like that. Okay. And when you write about chemical reactions, how you have N2 plus O2 giving 2NO. So N2 and O2, that is, we can write that nitrogen and oxygen combine to give nitrous oxide, nitric oxide, NO. That is N2 plus O2 giving 2NO. That is 1 mole of nitrogen molecule and 1 mole of oxygen molecule combines to give 2 moles of nitric oxide molecule. So this is how this is. So N2 and O2, this is known as the reactants, and the reactants react to give the products. Okay. And the number of atoms on the right hand side, and that is on the reactant side, or the on the left hand side, that is the total number of atoms on the reactant side should be equal to the total number of atoms on the product side as well, because it's based upon law of conservation of mass. Mass can neither be created nor be destroyed. So that, because if the equation is not balanced, you need to balance that equation. So in this case, you have 2 nitrogen atoms And on the product side or on the right hand side, again, you have two nitrogen atoms as well. On the left hand side, you have two oxygen atoms. And on the right hand side also, you have two oxygen atoms. So if you just write the equation without balancing, N2 plus O2, giving NO, that will not be a balanced equation because you have two nitrogen atoms, and without a 2 here, you have only one nitrogen atom. We have to balance that. So in this case, I need to just add a 2 on the product side. So that will balance the equation because you have to make use of the law of conservation of mass. Mass can neither be created nor be destroyed. So that is how we are balancing a chemical equation. So when you write this equation, it just this is how you represent a chemical reaction. A lot of just is when you write this, a lot of information is stored in that chemical equation. From that, just by looking into that equation, you get a lot of information about that reaction. So what all information do you get from this simple chemical reaction? From this chemical reaction, this can be read in many ways. You have N2 plus O2 giving 2N. This can be read as, say, one N2 means a molecule of nitrogen. O2 means a molecule of water. Molecule of oxygen. NO means a molecule of nitric oxide. So here, N2 means I have one nitrogen molecule combined with one oxygen molecule to give 2 molecules of nitric oxide. So this can be read as 1 molecule of nitrogen combining with 1 molecule of oxygen to give 2 molecules of nitric oxide. This can be read in the mole concept as well. That is, 1 mole of nitrogen molecule combining with 1 mole of oxygen molecule to give 2 moles of nitric oxide molecule. See, this equation can be read in many ways. So one method is 1 molecule of nitrogen molecule combined with 1 molecule of oxygen give 2 molecules of nitric oxide, NO. Or we can read as 1 mole of nitrogen molecule combined with 1 mole of oxygen molecule to give 2 moles of nitric oxide. And what is the weight of 1 mole of nitrogen molecule? 1 mole of nitrogen molecule with 1 mole of nitrogen. So what is the weight of one? If I say what is the weight of 1 molecule of nitrogen molecule, or 1 mole of N2? Atomic mass of nitrogen is 40 AMU, and a nitrogen molecule made up of 2 nitrogen atoms. So 14 plus 14, 28. So 28 AMU is the atomic mass of nitrogen. 14 is the atomic mass of 14 AMU is the atomic mass of nitrogen, and 28 is the molecular mass of N2. So if you want to calculate the mass of 1 mole of nitrogen molecule, that is 1 mole of N2, its weight will be 28 grams. And molar mass of oxygen, O2, will be 32 grams. So 1 mole of nitrogen will be weighing 28 grams. 1 mole of O2 molecule, O2 will be weighing 32 grams. That's molar mass. So 28 of grams of nitrogen combined with 32 grams of oxygen, giving 60 grams of NO, because you have 2 moles. 1 mole of NO will be weighing 30 grams, nitrogen 14, oxygen 16. 14 plus 16, 30 AMU is the mass of 1 molecule of NO, nitric oxide. So what is the mass of 1 mole of NO? It will be 30 grams. And 2 moles, 30 into 2, 60. So 60 grams. So again, we can say that the mass of total mass of the reactant will be equal to the total mass of the product. 28 plus 32, 60. That also should be conserved. Total mass should be conserved. So yeah, 28 grams of nitrogen combined with 32 grams of oxygen give 60 grams. So this equation can be also expressed in terms of volume. 1 mole here, 1 mole of nitrogen. And what is the volume occupied by 1 mole of nitrogen molecule under STP condition? That is 22.4, the molar volume 22.414. And what is here again, you have 1 mole of oxygen molecule. What is the volume occupied by 1 mole of oxygen molecule? Again 22.414. And here you have 2 moles of nitric oxide. And what is the volume occupied by 2 moles of NO? STP 2 into 22.4, that is 44.8. So this equation can be also extended 22.4 liters of N2 combining with 22.4 liters of O2, giving 44.10 liters of N. So this is how you can express. So a simple chemical equation can be read in many ways. It contains a lot of information. So you can say chemical equations from this equation, you can say how many molecules of each substance are reacting, or how many moles of each substance are reacting, or how many how much mass of each substance are reacting, or how much is the volume of the reactants, and how much is volume of the product. So a chemical equation is not simple as that. It contains a lot of information. So this is what I will be discussing. This is what I discussed in the fundamentals of chemistry chapter. So in this third class of discussing about the fundamentals of chemistry, I discussed about the mole concept. I discussed the concept of atomic mass. I discussed about the concept of molecular mass. I discussed about the concept of STP condition, and I discussed about the basis of how to write chemical reactions. So that's about the classes discussing about the fundamentals of chemistry. So if you need any more classes discussing any other fundamentals of chemistry, which I haven't discussed in these three classes, just to mention it in the comment section. I'll be happy to discuss that. So this is about the classes dealing with the fundamentals of chemistry. Okay, so thank you all.